So for this one here, we've got an ion of mass 6.5 times 10 to the minus 15 kilograms. And the charge is some unknown magnitude. It moves in a straight line through a region of space in which we have a uniform magnetic field which points out of the paper. This is my attempts at uniformity. And it also has an electric field which points towards the top. And I have a feeling this isn't very straight, so I'm just kind of going to redraw this a bit here. So let's try to straighten this up a bit. I apparently have some disorder that leads to things not being very straight here. Alright, there's our B field. Alright. So we've got an E field which points upwards. So that's going to deflect the charge either upward or downward depending on the sign. And we've got a B field that, that comes out of the page, which again is going to deflect the charge in one direction or the other. So this doesn't tell us our, this would tell us our magnitude, but not necessarily our sign. And then it travels into region 2, in which only the magnetic field is present. So there's no E field this time. And the particle is deflected into a circular orbit. And this direction. So already we can get our charge from our B field there. Okay, so our A is indicate the forces which act on the ion at point P1 in region 1. Okay, so assuming a positive charge, then our free body diagram in area 1 is going to be an electric force going this way. And then as it's traveling in a straight line, we'll have to have a magnetic force going in the opposite direction and actually equal in magnitude. Okay, and we can write these as well. So this is going to be QE, and our magnetic force is going to be QV cross B. And if we use our right-hand rule, so we point, so our velocity is this way. So if we point our fingers in the direction of the velocity and our palm in the direction of the B field on our right hand, and then our thumb will point in the direction of the force. So we can see that the force will point downwards. So this will be minus QVB in the y-hat direction. And we're given our E field is in the positive, so this will be QE in the y-hat direction. So that all checks out. And we can already see now what the charge on the particle must be, as when it enters into circular motion, our force must be this way, right? So For B, what is the ion speed at point P1? P1, so this would be P1 here. We are given various factors here actually. So, all right, so we have F net is equal to QE minus QVB, which equals 0, so that's in the y direction. And in the x direction, it would also be 0, but that's okay. In the y direction is all we're concerned with, so QE is equal to QVB. We can see that the charges will cancel. And so our velocity is just E over B. And we're given that this is 2,500 newtons per coulomb over 5.0 Tesla, which comes out to be 500 meters per second. So there's our speed. C, indicate on the diagram at point P2 in region 2 the direction of the force. So I kind of already did this, but if we're entering into circular motion, then we know that the force has to be towards the center of the motion. And then so D is Q positive or negative. So our force from our magnetic field is minus QVB y hat. But from our free body diagram, we can see that our force has to be in the positive y direction, so Q must be negative. Right, and that way our force will be, so it's like Q is minus Q, where Q is the absolute value of the charge. So then F would be QVB in the y hat direction. That way we can get our centripetal motion. Okay, so now checking through our solution here. So we get an electric force and a magnetic force, which are directly opposing each other. We can use this to solve for a velocity is 500 meters per second. Our direction of our force at P2 must be centripetal, so it must point towards the center of the circular motion. And for this to be the case, it has to be a negative charge. And so that looks good.